Section 1.2, radicals and rational exponents. So our objective is to simplify expressions involving radicals and rational exponents. So first we need to talk about what is this idea called a radical. Okay, a radical expression is an expression that contains, so expression that contains what we call the radical symbol. Okay. The radical symbol, I'm going to draw it nice and large here because we're going to be talking about it, looks like that. There is our radical symbol. You've seen this symbol before. It is not the divide box because of this little extra tail, but you've seen this symbol before when we've taken the square root of 9. Because that is the radical symbol, and the square root of 9 is a radical expression. Okay. But now we're not only going to be dealing with square roots, we're going to be dealing with what we call higher power roots because we're going to have other indexes. Okay, so you might be wondering where the index is. Okay, many times we see a little number inside the little crook of that arm, and that is what we call the index. The index tells me what power we are taking the base to. Okay, and then the radicand is whatever's inside of here. So the radicand is right there. So there is our what's called the radicand. Okay, so if you remember from exponents, okay, we take a base. So for example, I take a 3. If I take a 3 to the second power, so again, let's do a little vocabulary. The 3 here is my base. The 2 is referred to as the power or the exponent. And this tells me that I'm multiplying 3 times itself twice. And since 3 times 3 is 9, then the square root, the index in here is a 2. Notice I put that little 2 in there. My index is a 2. And when the index is 2, we tend to not write it. So an index of 2 is assumed. It's just assumed the index is 2 if it's not written. So since 3 to the second power is 9, the square root of 9 is 3. What number, this is asking, what number here do I take to the second power to get 9? It works that way for whether your index is 3. So for example, you might see we could have the third root of 27. So this would be written as the third root of 27. Or third, we tend to use the word cube, the cube root of 27. I'm looking for that same idea. What number to the third power, let's not put an equals there because it's not really equals. What number to the third power equals 27? Kind of out of room there. Sorry guys, should have left a little more room. What number to the third power is 27? That's what this radical expression is asking because we're doing to the third power. We could be dealing to the fourth power, to the fifth power, so forth and so on. So since we're going to be dealing with that power idea, we need to review our properties of exponents. Okay, so this was, in previous courses, you probably went over these powers of exponents. You do not need to really worry about memorizing these names over here. You just need to identify when you can use it and how you use it. And in many cases, if you forget these rules, I like to call these rules shortcuts. So properties of exponents, or AKA shortcuts, because many, if not all of them, you can get to without using them. For example, the product of powers. Basically, this is saying if I have the same base, notice these are both base A to the m times A to the n. Bases are the same. It's important to note here, base is the same. Okay. You add the exponents. But if I don't remember that, I can get to it regardless if I know what an exponent is. Because I know 3 to the fourth is multiplying 3 4 times. So there's my 3 to the 4th. And then I want to multiply that times 3 to the 2nd, which is multiplying 2 3s. So really, my base in this case is 3, but how many times am I multiplying it? 1, 2, 3, 4, 5, 6. 6 times. So I end up with 3 to the 6th. Now, if I remember this shortcut, I can save myself writing this all out. And if your exponent is really big or a fraction, and how do I write 3 multiplied times itself a half a time? That's a lot harder to do. Then this does become a rule, okay? Meaning that it's really hard to write it out long way. But you can always attempt to write an example of it long way to remember what to do, okay? The same holds true for the quotient of power. Again, so here we're dividing. Again, the base is the same. Oh, I wanted that in red. Sorry, guys. Base is the same in this case as well. See, base A, base A. So if the base is the same, like 3 to the 4th divided by 3 to the 2nd, again, I can write that out longhand. 3 to the 4th is 3 times 3 times 3 times 3. There's 4 of them. Divided by, now I have 3 to the 2nd. 3 times 3, okay? Now I can split this up and write it as 3 over 3 times 3 over 3 times 3 over 1 times 3 over 1, because I don't have any more 3's in the denominator. I only have 2 3's in the denominator. Well, this 3 over 3 right here, this first 3 over 3, sorry, that simplifies to 1. 3 divided by 3 is 1, and I'm just left with 3 times 3, which lo and behold is 3 to the 2nd. So our rule tells us that we can subtract the exponents. So instead of going through this whole process, if we remember the rule, when you divide with the same base, you subtract the exponents. When you multiply with the same base, you add the exponents. Okay, the next one is the power of a product. Notice here they don't have the same base. What they do have is the same exponent. They both have an exponent of n. So if I had 3 times 4 to the 2nd, yes, I could multiply 3 times 4, which is 12, and then take that to the 2nd, okay? Or I can take 3 to the 2nd, which is 9, times 4 to the 2nd, which is 16, and do it that way. Regardless, I'm going to get the same thing, which is 144, okay? Where this is useful, it's not super useful when it's 3 and 4, but if I have 3a to the 2nd, again, that's a multiply in there. That's an implied multiplication. That's the same as 3 to the 2nd times a to the 2nd. Okay, that's much more useful in this situation because then 3 to the 2nd is 9 times a to the 2nd. Okay, so these are mathematically equivalent. Okay, so again, the bases aren't the same, but they're multiplied, their power is the same. So here we have the same exponent. Okay, next one, the power of a quotient. For all real numbers, A and B. So here this is very similar. Again, we have like these two are very similar. Okay, same bases. We're either adding the exponents or subtracting the exponents. These next two are very similar. They're really almost the exact same rule. If I'm multiplying with the same exponent, that exponent is going to go to each piece. And when I'm dividing with the same exponent, that exponent is going to go to each piece. Okay, so here, which is then useful when I have fractions. 3 divided by 2, which is 3 halves, to the 2nd power. That 2nd power goes to the 3, and it also goes to the 2. Fair warned, this is not the distributive property. All this is using is the fact that I know that 3 over 2 to the 2nd means 3 over 2 times 3 over 2, which means in the numerator I have 3 times 3, and in the denominator I have 2 times 2, which therefore is 3 to the 2nd over 2 to the 2nd. Again, if you don't remember the rule, you can get to it without. Okay. Same with this one up here. If I have 3 times a to the 2nd, that just means 3 times a times 3 times a, which 3 times 3 gives me the 9, and a times a gives me the a to the 2nd. Okay. The power of a power. Okay, here I have one single base, a, but 2 separate exponents, but parentheses here, okay? Again, you can get to this one without using the rule if you don't remember the rule. Because here I have 3 to the 4th to the 2nd. So that means I'm taking what's inside here and taking it to the 2nd power. So that means I need to write it twice. 3 to the 4th times 3 to the 4th. Well, 3 to the 4th is 3 times 3 times, so I can write it out 4 times. And then the second 3 to the 4th would be 1, 2, 3, 4. So really, I'm multiplying 3 8 times. Okay. This next one is just one you're going to have to remember. I'll show you why it works, but basically any number, any base to the 0 power is 1. Reasoning for this. Okay, I'm going to show you why it works so we kind of understand. If I have 4 to the 2nd divided by 4 to the 2nd, okay, well, that's 4 times 4 divided by 4 times 4, which is 16 divided by 16. Well, 16 divided by 16 is 1. If I come back and use this quotient property, bases are the same. They're both 4. I should be able to subtract my exponents, right? So I should be able to take 4 and take the 2 minus the 2. This exponent minus this one. Sorry, that's really tiny. Well, 2 minus 2 is 0. So 4 to the 0. For this rule to be a rule and always work, anything to the 0 power has to be 1. Anything to the 0 power has to be 1. For that quotient rule to, in fact, be a rule, for it to be a rule, it has to work all the time. Okay, so for it to work all the time, it has to always work, even when the numerator and denominator have the same exponent. So that's where that comes from. And that's the same with this negative exponent. This one's a little harder for us to remember for some reason. We tend to want to take this negative exponent and do something crazy with it, like make the whole number negative, or basically this means I'm taking 4 to itself a negative number of times, which is really not possible to write out. But a negative exponent takes the reciprocal. Okay, if you remember the reciprocal of like 1/5, the reciprocal of 1/5, I'm not going to use equal because they're not equal, is 5. And the main reason is because if I multiply these, I end up with 5 over 5, which is 1. Reciprocals always multiply to 1. That's the definition of reciprocal. They multiply to 1. Okay, so a negative exponent takes the reciprocal. So 8 to the negative 3 is going to be 1 over 8 to the 3rd. The reason for this also stems from this quotient rule as well. Because if the numerator is more than the denominator, so if I have, let's say, 4 to the 2nd divided by 4 to the 5th, okay, if I use that quotient rule, it would be 4 to the 2 minus 5, which would be 4 to the negative 3. Well, if I don't use the quotient rule and write it all out, switch colors, that would be 4 times 4 divided by 1, 2, 3, 4, 5 fours. So then I'd end up with 4 over 4 times 4 over 4, if I separate this out, times 1 over 4 times 1 over 4 times 1 over 4. Well, that's 1, that's 1. I'm left with 1 over 4 to the 3rd. So therefore, this and this have to be mathematically equivalent, again, for this quotient rule to work. This one right here. No, sorry, this one right here. Scratch that. The quotient of powers to work. Anything to the negative exponent. Okay. All right, so example 1. So we're going to determine what real number 3 to the 1/2 is. So now we're going to get into, again, here my base. 3 is my base. 1/2 is my exponent. And we need to make sense and try to figure out what in the heck does that mean. Okay, so to do that, we're going to say, let's take this 3 to the 1/2 and let's square it. Let's just see what happens. So I'm going to take 3 to the 1/2 and square it. What property of exponents could you use to simplify this expression? So I have one exponent, 2 bases, one base 2 exponents, scratch that. Okay, and I have a power. Which one over here looks like that? It looks like maybe this guy. There's my one base, exponent to an exponent. Power of a power. So that would be the power of a power rule. Again, you don't need to worry so much about remembering the name of it, but I'm going to write it down, which tells me a to the m to the n is equal to a times m times n, right? We can go back and look. Yep, I multiply m times n. Okay. All right. Use that property to simplify the result of squaring 3 to the 1/2. So we're going to, sorry guys, I didn't leave a lot of room for this, but we're going to fit it. Oh, 3 to the 1/2 to the second tells me I take 3 to the 1/2 times 2. 1/2 times 2 is 1. 3 to the 1, which is just 3. So when I take 3 to the 1/2 and square it, I just get 3. Hey, C. The definition of square root says that A is the square root of B whenever A squared equals B. Okay, so let's go back. Definition of square root. So that A is the square root of B. A equals the square root of B whenever A squared equals B. Okay, so basically we took it 3 to the 1/2 and squared it, and we got 3. So let's look to see what place is which. My B, it looks like, is the 3. Oh, I don't know why that did that. And my A is the 3 to the 1/2. So what does that tell me about 3 to the 1/2? If we go back here and look this guy, that tells me that A is 3 to the 1/2. That 3 to the 1/2 equals the square root of my B is 3. 3 to the 1/2 equals the square root of 3. Generalize your result. Do we think this will work for everything, or do we just pick 3 and it only worked for 3? If you notice, I didn't actually do anything with the 3. The 3 just followed along. So I'm thinking this is going to work. Now I'm thinking I know it's going to work. If this was a 5 instead, would it change anything? If this was a 10, would it change anything? So basically, any base, let's do something other than any number to the 1/2 power is going to equal the square root of that number. So the 1/2 power equals the square root. Okay. Now I want you to go ahead and do this your turn. Okay. So then how would you define a to the 1/3? And in general, a to the 1 over n, where n is any integer greater than 1. Explain your reasoning. So I want you to come up. Do you think this will generalize to any fraction like that, like 1/3, so forth and so on?